This video demonstrates the multi-source monitoring framework developed within the CHOReOS project. The multi-source monitoring framework integrates three different solutions. Each solution provides monitoring facilities for a specific kind of source. The integration among the three solutions relies on a distributed service bus called DSB that provides shared and distributed communication channels for the monitored events. In particular, we are dealing with the following sources: platform monitoring, which identifies crashes and other instabilities from the hosting platform. For example, this first source can provide information about the node utilization, and based on such information, is it possible to properly allocate resources or pinpoint to causes for SLA violations. BSM monitoring focuses on the messages exchanged among the cooperating services. It analyzes the temporal sequence of messages at the services level, looking for both functional and non-functional violations of the choreography. Event monitoring relies on a generic event-based monitoring called Glimpse that is conceived to aggregate the notifications generated from multiple instances of the other sources. In other words, it provides a complex event processor that correlates atomic events produced from different abstraction levels. This demo is based on the use case passenger-friendly airport that has been already introduced in the WP3 demo. We will show how we can combine the runtime assessment by the BSM of the CHOReOS for a service in the choreography with the status of the virtual machine hosting that service, as revealed by the platform monitoring. The notifications produced by the BSM and by the platform monitoring will be dynamically correlated at runtime by means of the CEP. The demo will be structured in 4 parts. Here we start with the configuration of the CEP. So we first start the CEP and then we connect it to the DSB. Then we load a set of rules on the CEP matching the complex event we are interested in. For this demo we loaded 3 rules. The first rule correlates an SLA violation raised at the service level with a notification reporting that the hosting platform is overloaded. The rule matches when the service that violated the SLA is hosted on an overloaded platform. In this case, a redeployment of the service is requested. The second rule correlates an SLA violation raised at the service level with a normal operation of the hosting platform. If this rule matches, a check on the service behavior is requested. The last rule correlates an SLA violation raised at the service level when no notification is received from the hosting platform. In this case, we assume that the status of the hosting platform is critical. Then again, a redeployment of the service is requested.
Work Package 3 demo and focus our interest on the weather forecast service quality assessment. We assume that all the services involved in this choreography are already deployed on top of the CHOReOS middleware. And now let's present the storyboard of this demo. First, we start the BSM. Second, we connect the BSM to the DSB. Third, we load the SLA for the weather forecast service. Once the choreography is enacted, we wait for a potential SLA violation. If the SLA violation is confirmed and then observed, we forward this alert to the Glimpse CEP. Okay, now let's start up the BSM. To do this, we use the startup script. Okay, now we can say the BSM is started. An interesting feature of the BSM is that it exposes its main administration services as web services. We need to parameter the monitoring to access the DSB node on which the weather forecast service is deployed. At this step, the services are running on top of the CHOReOS middleware. The monitoring is activated, and now we need to prepare for an SLA for the weather forecast service. Back to the initial choreography of this demo, of the unexpected arrival of a flight, we will focus on a single choreography task that is between the weather forecast service and the airline ground staff meet. Let's assume that the airline ground staff meet and the weather forecast company agreed on a 2-second response time for getting weather information. Thanks to the BSM functionality, we can now load the service level agreement that was defined between the weather forecast service and the airline ground staff meet. As you can see here, the latency is stated at 2 seconds. Back to the monitored choreography, a second row report T3-T4 generated from the exchange between the weather forecast service and the ground staff meet confirms the SLA violation. Here we'll focus on the events that goes from the BSM to the Glimpse event processor. The complex event processor is accessible through a weblog. In this weblog we can see the SLA alert generated earlier. If we focus on the information of this SLA alert, we can see that the status of the alert is stated as observed. Later, the CEP can interpret this alert according to the rules that were defined. Right now, the choreography is enacted, and we are waiting for row report events coming from the DSP node. Row reports are events generated from the DSP where services are deployed to the BSM. The exchange between the airline ground staff meet and the weather forecast service generates two row reports T1, T2 and T3, T4. T1, T2 is the row report from the service consumer to the service provider, while T3, T4 is the row report representing the answer from the provider to the consumer. Now the choreography is enacted. If we wait, we can see the first T1, T2 row report that is generated when the airline ground staff meet calls the weather forecast service.
In CHOReOS, we also monitor the environment where choreographies are executed, that is, the virtual machines where services run. This enables us to automatically allocate and deallocate cloud resources on demand, as well as to better identify and correct problems such as SLA violations. This is based on Ganglia, a widely used grid monitoring system. Ganglia and the notification daemon are installed on every new CHOReOS node. Ganglia periodically extracts metrics on the current status of the node, and whenever a potential problem is detected, a notification is sent to the Glimpse complex event. In this demo, we are discussing one particular scenario of the passenger-friendly use case. Within the scenario, right now we are concerned with the load status of the machine where the weather forecast service has been deployed. Excessive load on this node may lead to other problems, such as the SLA violations we discussed before. This part of this demonstration involves very few steps. We might start with the choreography enactment, the creation of the virtual machines by the node pool manager, and the deployment of the services. However, we should note that the platform monitoring is not directly related to any specific service or choreography, and its deployment may have happened much before the choreography we are interested in even existed. Therefore, we will not discuss these steps, and instead will take an existing machine where we may deploy a service such as the weather forecast service. We will see that this machine is currently idle, periodically notifying the complex event processor that it is alive. We will then create an excess load on the machine and verify that in turn it sends a notification to the complex event processor. Ganglia provides a lot of information, but right now we're only concerned with load 1, the load average for the last minute, so we can filter for it. Currently, this value is 0.14, as we can see here. This is a very low value. This means this machine has nothing special to report. Therefore, if we check the log for the complex event processor, we will only see stuff like this, periodic messages indicating that the machine is alive. Now, what we're doing is we're going to run this script which just runs 3 endless loops in parallel. This makes the load average on the machine rise very quickly, as we can see here. It's now 0.52, now it's 0.72. Let's see what Ganglia says about it. Now, Ganglia does not collect data every time it's queried. It polls the data periodically, which means there may be some delay before it notices the increased load. but as you can see, it detected a load of 1.07 now, which is higher than the maximum we have established before. This makes the system send a notification to the complex event processor, suggesting something might be wrong with this machine. As we can see, we have a notification here stating that we expected that load1 parameter would stay below 1, but it actually went above that to 1.07. The log does not show this, but it is important to highlight the fact that this message includes the host name of the machine that originated this message. Once again, the information provided by Ganglia is related to the virtual machine, not to any service or choreography. It is up to the complex event processor to correlate such information to the corresponding services and choreography roles. It is easy to correlate machines and services just by comparing host names. It is harder to identify choreographies that might be affected by some machine behavior, since a single service may perform multiple roles on multiple choreographies, and a single role may be played by different service instances on different moments in time.
In the first part of this demo, we started the CEP, connected it to the DSB and loaded a set of compare rules on it. Then we showed how both service level and platform notifications are generated. In the following, we show the matching of such notifications with the rules previously loaded, and the specific reaction foreseen for each complex event. Here we see the matching of the first rule, and here the matching of the second rule with its foreseen reaction. Finally, we show the verification of a complex event matching with the third rule. This concludes our demo. For more information, please visit our website www.choreos.eu.